Well, coming to you live from the UPrep gym as I am not being a bad father and ignoring my daughter's game. This is actually the 6th grade game. My daughter plays next game. But it's a perfect time to talk to you about randomness, probability, and simulation. All right? Because as we go through this, we're going to talk like probability. If you ever heard of like the kid who has the hot hand in basketball, like it's unbelievable. You can't stop him. It's a hot hand. There's some truth in that, but there's also a sense that, or the flip side is, wow, they've missed 5 in a row. They're due to make a shot. All right, this all gets the idea of probability, randomness, and we'll do simulations to mimic these things. So with probability, just a pure definition of probability is probability is equal to the number of ways of what we want, out of, so divided by, all possibles. All right, and you've seen this in the past when you're looking at the likelihood of something happening, like rolling a die. If you're rolling a die, so here's my little dice right here that I have. There's my cube. All right, what's the probability of rolling a 1? Well, there's only one side, so let's say this side just has the 1 dot on it there. All right, there is a 1 chance out of 6 to get a 1. All right, if you're rolling 2 dice, for those of you that are big Settlers of Catan fans, you know that the robber gets moved if you roll a sum of 7. And so you think, well, how many ways can that happen? You can roll a dice and you can get a 1 and a 6, 6 and a 1, 2 and a 5, 5 and a 2, 3 and a 4, 4 and a 3. That is, there are 6 out of 36 ways to roll a sum of 7. All right? So when we're talking about probability, that's what we're talking about. Another way to think of it is this. There we go. It's the chance process, or the process. I'll write chance. It's the chance process of something happening in the long run, and it's the proportion. It's the proportion of ways I want it out of all possible. So it's kind of the same way. But probabilities themselves, the lowest they can be is 0. So and a probability at most can be 1. You can never have over 100% chance, or you can never have a chance over 1, nor can you have a chance less than 0. All right, when we're talking then about this randomness and then the myths of randomness, the idea that probability seems straightforward, a lot of people just don't understand, though, what's going on. Let's break here for a second. Let's say you're flipping a coin, and you get tails, 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 all in a row. And then here's the next toss of the coin. The question is, what's the probability that tails comes up? It's always going to be 1/2, because it's always a half chance. So it could be tails, it could be heads. Just because you get 4 tails in a row does not mean that you're now due for a heads to roll. So this is an idea that we're going to get to that's called the theory of large numbers. But basically this, as you do something over and over and over again, repeatedly, the probability of an event, so if you actually roll a dice thousands of times, the probability that the side of the dice is equal to 1, so this is a capital P for probability of, it's a function, the side of a dice is equal to 1 is equal to 1 out of 6. We know that is theoretical, but if you're going to do this experimentally, you're going to roll that dice thousands and thousands and thousands of times, and over time, the probability is going to average out to be that 1/6. So let's say I flip a coin, or let's say I roll a dice, all right? And I'm looking at this, and this is probability. And the lowest it can be is 0, and the highest it can be is 1. And I roll that dice the first time, my first roll, and let's say I get a 1. So it's happened 1 time out of 1 roll. And then second roll, it doesn't happen, so my probability comes down a little bit. So it's one, sorry, not to there, it actually comes down to here, because now it's happened one roll out of two, or it's a half. All right, and then a third roll, it's also not there, so then I'm down here, but then the fourth roll, maybe I get another one and bounces up. So each time, my probability, but then over time, in all these rolls, it's going to average out down here to the 1/6 probability, because the likelihood of rolling a 1 is 1/6. So it might take a while for it to bounce out, but after we've done this thousands and thousands of times, my likelihood then approaches the actual theoretical probability. This is what we would call experimental probability, and we could run a simulation to do that. That was loud. The law of averages is then this other thing, and it's usually often more of a myth, the law of averages. And it gets back to the idea of randomness, that somehow you're like due for something to happen, that based on the law of averages, eventually something can happen. And that's actually the opposite. The law of averages says that anything can happen. And if it's really strictly due to probability, it's possible it could never happen again. So it doesn't have to necessarily average out. So how can we run a simulation? Let's say we have a random digit table, and we've pulled these numbers off of a random digit table. So we have all these numbers here, and we're simulating rolling. We're going to stick with this idea of a dice. Rolling a 1. All right, I first need to assign each of the dice numbers, and we're going to assign them 1 to 1. So a 1 is equal to a 1, a 2 is equal to a 2. And then we're going to ignore 7, 8, 9, and 0. We ignore because they're not parts of the rolls of a dice. And then we go along and say, okay, we ignore this one. Here, let me change my colors. Ignore, so I've got 1, 2, ignore, 3, 4, 5, 6, ignore, 7, 8, 9. So in this set, based on my simulation, there is a 1 in 9 chance of rolling a 1. Now again, you've had dice before, so you know the probability is actually 1/6. But this comes into play with other more sophisticated things that we're going to do, where maybe you can't necessarily, likelihood of having a baby that's a boy. You can't just grab a whole bunch of women and have them give babies and then count how many it happens. We have to run type of a simulation, or maybe look at some past data. And that's what the purpose will be of running a simulation, to see, well, what's the likelihood that this actually should have happened based on chance. So here's a question I have for you want you to think and ponder your way through. And you're going to put this in the reflection response. But the question is this: as you think about two people, so think of a room of, let's say we have a room of 30 people, randomly selected and put in that room. What's the likelihood that at least 2 of them have the same birthday? It's actually a very complicated problem. The answer is going to surprise you, but I want you to take some time tonight and think about how you might go about trying to simulate something like this happening. Thinking about the random digit table. Jot down some ideas, put those in the reflection response, and we're going to actually run this simulation in class. And then we'll calculate the actual theoretical probability. So first we'll do a simulation for experimental, and then we'll run the actual theoretical. That's it for now. Goodbye from the UPrep gym.